So good morning or good afternoon to everyone. I'm Michelle Dunn in the Office of the Associate Director for Data Science at NIH. It gives me great pleasure today to introduce Dr. Bryan Caffo, who is the professor in biostatistics at the Johns Hopkins School of Public Health here, who is my neighbor here in Maryland, down the street. He is world famous as the co-creator and co-director of the Coursera Data Science Specialization. And if I remember correctly, his group was even the one that suggested the idea of a specialization to Coursera. He is also the co-creator and co-director of the SMART group. SMART stands for Statistical Methods and Applications for Research in Technology. And this group focuses on statistical methods for biological signals. So Bryan's research is in statistical computing and generalized linear mixed models with applications to neuroimaging, functional magnetic resonance imaging, and image processing in general. He is well entrenched in the analysis of big data, leading teams to work in prediction competitions. A couple of the notable ones that his team has done well in are the ADHD 200 prediction competition, which they won, and the Heritage Health prediction competition, which they got 12th place in. So congratulations on those. Dr. Caffo has been given numerous awards, and I list a couple of them here. The first one is the PCASE Award, which is the Presidential Early Career Award for scientists and engineers. This is probably the most prestigious award that can be given to an early career researcher. He's also won awards for teaching and for mentoring. So with that, I will turn it over to Dr. Bryan Caffo. Bryan, thank you very much for being with us today.
Thanks, Michelle. I hope everyone can hear me. Thank you for inviting me, and thanks for Crystal for doing all the organization. So my topic today is exploratory data analysis, and I'm going to talk about this more like an instructor of an exploratory data analysis because it's an area that I use a lot, but it's certainly not an area that I do a lot of active research in. I do have one notable exception. So my former PhD student named Bruce Swihart, who's a really brilliant guy, he works at the NIH now. He wrote a paper that was really about contributing the idea of using heat maps to perform visualization for longitudinal data analysis. And he has probably the best title of any paper I've ever written for certain. It's called Lasagna Plots, a saucy alternative to spaghetti plots. So if you want to see like a nice little paper on visualization, check out Bruce's paper. But the fundamental idea, I'll just cover this really quickly, is that with spaghetti plots like in this, hopefully everyone can see my cursor. If you can't, maybe someone let me know. Like this big black mess over here is just a lot of overplotting from spaghetti plots. If in cases like this, you might want to do something like put it into a heat map where you could actually see trends. Like here, we were investigating sleep disorder breathing and some EEG signals, and you see some interesting missing data patterns. You also see, just generally that the sleep disorder breathing subjects have like more red than the non-sleep disorder breathing subjects. Anyway, it's a nice little paper. It's on PubMed. Mostly what I'm going to talk about today is sort of principles of exploratory data analysis. If you want kind of a lot of practical information about exploratory data analysis, in other words, if you want to know how do I do exploratory data analysis in R in specific, or Python in specific, or SAS in specific, or something like that, certainly the best resource for R, I would say, is Roger Pang's Exploratory Data Analysis with R book. It's just all about how do I do it, not why do I do it, or what are some of the guiding principles of how you do it, which is what I'll talk about today. He also has a Coursera course. I should make a small comment. It was actually Coursera that came up with the idea of a specialization, but we jumped on it rather quickly, to our credit. And then, of course, the Bible of exploratory data analysis is John Tufte's book, if you can find a copy of that. But these two this book by Roger Pang and his course are very good, like practical how-to type books. And today, what I'm going to cover are things that are really don't apply across however you're doing exploratory data analysis, whether you're doing in Python or R or whatever. So let me just start by saying what exploratory data analysis is, and if I'm going to define what exploratory data analysis is, I should define what statistical activities are not exploratory data analysis. So the traditional dichotomy that people talk about is to differentiate between exploratory data analysis, EDA, and confirmatory data analysis, CDA. So exploratory data analysis focuses on discovery and hypothesis generation, whereas confirmatory data analysis tends to focus on hypothesis confirmation. Exploratory data analysis still controls error rates and performs uncertainty quantification, but it tends to do that much more loosely. Confirmatory data analysis tends to focus on formal inference and prediction techniques. Both of them can use the same methods. The difference is exploratory data analysis tends to be more free-form and less structured, and I liken it to sort of improvisational jazz. And then CDA is a little bit more prescriptive, protocolized, and planned. And so I have a picture of a symphony down there. So I think you know, that kind of differentiates the idea behind the two techniques. I would say in general that data analysis falls on a spectrum between the highly prescriptive and formal confirmatory data analysis sort of ideal, and that's probably most realized in the area of highly regulated clinical trials. So where clinical trials tend to be highly protocolized and regularized, especially in drug development. And then, you know, there's some areas like high throughput technological measurement areas like genomics tends to fall in this category, where things are a little bit more exploratory in nature. And so I think things, though, typically most analyses fall in some gray zone between the two. So I actually often think the EDA versus CDA division is more useful conceptually than practically. And then, you know, I would say, you know, maybe an alternate dichotomy, if you really have to have a dichotomy, is to think about whether or not you're using strongly phrased scientific hypothesis to drive your research versus doing purely empirical studies. I think that's a more useful division. But you know, and I actually put some papers down here that discuss some of these issues. For example, this paper by Kell and Oliver that says, here's the evidence, now what's the hypothesis? And it talks about the roles of inductive and versus hypothesis-driven science in genomics. And then this great blog post by Simply Statistics where it says the key word in data science is not data, it's science, therefore, you know, obviously promoting this kind of strong hypothesis-driven research agenda. And then, again, I haven't really defined EDA or really gone into much about the specifics of EDA, but I want to, you know, put one of the biggest points that's generally brought up about EDA versus CDA now is the idea of doing a lot of exploratory analysis and then presenting only the final step as if that was the only step that you did. And that particular process is called p-hacking or data, you know, or phishing or that sort of phishing expeditions or that sort of thing. And it generally falls under the rubric of the more you use your data for hypothesis generation and exploration, the harder it gets to really control the error rates on the same data for some sort of final analysis. And I would say there's been a lot of research in the past couple of years on the extent and consequences of this problem. So probably most notable was Iannides' very famous article that said why most published research findings are false. I found this other great article on the extent and consequences of p-hacking in science, which I thought was also very interesting. And then Jeff Leek and Leah Jaeger, who are here in the department with me, both really great researchers, you know, really tried to put some numbers on this idea of the rate of false positive findings in science, and they gave an estimate of the false discovery rate in the top medical literature. So I would suggest you read all these literature and maybe even in the broader literature in this area if you're interested in this problem on using exploratory data analysis too much to the point where it sort of biases your confirmatory results. But that is a big warning about you know, a big no-no is to do a lot of exploratory data analysis and then present the final step as if it was confirmatory. So now let me actually get to the topic of exploratory data analysis. So I'm going to give, this is a shout out to Jeff Leek, who teaches exploratory data analysis in his class, so I borrowed a lot of slides from him. He had this great breakdown of what he thinks of as the steps in an exploratory data analysis, and I think it's a really nice summary. And these are reading in the data, kind of figuring out the data. You know, after you read it in, you really just, you know, you need to figure out what the columns are, that sort of thing. Pre-processing it, looking at dimensions and making sure they measure up, especially if you have more than one data set that you're trying to merge together. You have to look at its values, make sure there's no weird values. You need to make tables and hunt for messed up values, figure out how missing data is coded. NA stands for missing data. How missing data is coded, how much missing data is there, is missing data coded consistently, and then you want to do a lot of plots. Plots are sort of the cornerstone of exploratory data analysis. And then the final step says, don't fool yourself. So today, and I'll talk more about that, but today really, these are the things I'm going to focus on. And there's a lot of content in exploratory data analysis, and a lot of content in these areas I'm not going to cover, but just in a 1-hour talk, I certainly can't get them all. So I'm going to spend a little bit of time on pre-processing, a little bit of time on not fooling yourself, and a lot of time on some basic guidance on creating plots. So let's talk about pre-processing. So we recently had a really wonderful talk from Jenny Bryan, who's a very notable data scientist who works at UBC, but then also just got hired by RStudio to be part of their educational and development team. And you know, there aren't a lot of great principles in pre-processing. There's almost like, it's almost like an artistic endeavor where you do it differently for every problem. And I think one of the things, if I'm thinking broadly about what her basic research agenda is to really try and synthesize this process into some general principles. And one general principle, she said, which I think is a very useful one, is to try and get everything into a rectangle. And she actually had this picture of a rectangle that with like angel wings on it. And you know, let me just expand on this a little bit. She really emphasized this idea that data wrangling is work. So if you spend a day or 2 days getting your data into a nice format, don't think of that as, well, I haven't even started working yet. The reality is you've done a lot of work, and some of the most important work. It's sort of like, yeah, the most exciting part of building a house is seeing it all come together and getting a lot of the nice finishing touches, but without laying the concrete for a firm foundation, the rest of the house is irrelevant. And so no one likes laying the foundation, but everyone thinks it's, you know, probably one of the most valuable parts of building a house. And I put that into this quote that would say, no one has ever said, I really regret getting my data into such a well-organized and thought-out format. So some basic things you want to remember is to try and save your steps while you're doing it. Use a version control system like Git. Try and engage in reproducible research as you're doing this. And then her point was also try and get your data into a rectangle. Name your columns with a sensible naming convention. Use names that are amenable to software packages, so don't put spaces and quotation marks and weird symbols and other things that aren't useful for coding in your names. You know, try and use capitalization and spacing in your column names like you're a programmer. No special features if you're using a spreadsheet. Don't put embedded graphs in your basic data format. Just try and split that out, split that process out. Even if you're using Excel to perform your data analysis, try and, you know, create copies of the data set, you know, where you record how you've created the copy and create graphs in different sheets. You know, don't use numbers for missing values is sort of one that comes up for me a lot, where people code missing values as 888, and then it gets read into a software package that doesn't recognize that and treats it as a number. It messes up the analysis, and usually you can detect that very quickly. But if you don't, then it messes everything up. Okay, and there's some tools. Again, I'm not going to spend a lot of this talk talking about tools, but in R, if you like to use R, there's a grammar of data wrangling that's coming about. It's still under development, but tools like dplyr and tidyr and purr and string R and these things are really making it a lot easier in R in specific. Of course, you can do data wrangling in any of the major analysis programs. Now let me talk about not fooling yourself. And the first thing I'm going to do when I talk about not fooling yourself is give a couple of kind of parables that go along with this. So the first is the famous one of the elephant and the blind men. This picture was off of Wikipedia. And it's the story of the elephant and the blind men is that, you know, the 6 blind men are investigating an elephant, and one of them touches its side and says it's a wall, and another touches the trunk and says it's a snake, and another, and you get the picture. They all got a very incomplete picture of the elephant. And this parable is used to illustrate several points, but I think kind of germane to our discussion is you're really, don't be like the blind man investigating the elephant, in that, or at least acknowledge that you're like that, in the sense that you only get to work with the data that you get to see. Another thing that's very common is this kind of bias that you get by finding something, finding a pattern and then pretending like it was what you were searching for to begin with. And this is most often described as shooting an arrow and painting a bullseye around where it lands. I actually found online a company called the Bullseye Painting Company. So I think they don't actually paint bullseyes. I think the bullseye is just their name. But at any rate, that's an important consideration when you're doing exploratory data analysis, is coming up with a chance finding and then pretending like it was something you were searching for all along. Then there's this famous Mutt and Jeff cartoon. I got this from Quote Investigator, where it's a drunk looking for his quarter underneath a lamppost, and it says, "I'm looking for my quarter that I dropped," and the policeman says, "Did you drop it here?" And the drunk says, "No, I dropped it 2 blocks down the street." And then he says, "Well, why are you looking for it here?" And the drunk says, "Because the light is better here." And the idea is that you're looking at the data that you have with the biases that it has, and we want to, as little as possible, be like drunks looking for our change under a lamppost, looking where there's light rather than looking where we need to be looking. And then, of course, the one that comes up the most and most people are aware of is this problem of multiplicity. And this is a great XKCD comic book. It's number 882. And in this comic book, someone says, "Jelly beans cause acne," and another person says, "Scientists investigate." And then the scientists look and says, "We found no link between jelly beans and acne." And then the person says, "I hear that it's only a certain color." And then they start investigating all the colors, and then basically all these panels are people investigating different colors. And then they find green does have an association, and then there's a news article that says green jelly beans are linked to acne. Of course, what this is illustrating that is if you keep looking for things in noise, you'll eventually find them. So just some example common ways you can fool yourself in exploratory data analysis. So these are some of the most common ways this can come up. And I'll relate them to the parables. So one thing is just issues with the data that you have. Can it even answer the questions that you're trying to ask? That's the elephant, the parable of the elephant and the drunk under the lamppost both discuss that point. Another thing is that even if you find a true thing, those true things may not paint a complete picture. That's, of course, the story of the elephant. The confirmation bias, the idea that you pretend like you discover things that you were just looking for ahead of time, and you just confirm them but ignore the evidence that refutes it. That's like painting the bullseye. False findings, are always a problem, just where you get chance associations. That's like the bullseye and the multiplicity. And then, of course, the problem of multiplicity is just repeatedly looking for things until you find something. So these are all the ways that you can fool yourself, and I think these problems are more pronounced in exploratory data analysis because we're not even pretending that we have some sort of strict error rate control that we're trying to go through. Rarely in exploratory data analysis do you have a highly protocolized version of what you're doing. So now so that discusses ways in which you can fool yourself. Now the rest of the discussion I'm going to spend entirely talking about interocular content, or other words, that the plots, things that hit you right between the eyes. And the idea is that plots are really the cornerstone of exploratory data analysis. And there's something about visual information that pictures really are often worth 1,000 words, and there's just something about them that can really speak to us and drive home points and help us discover things that just a table or a number or a written summary just somehow lacks. And I'll give a great example. Probably the most famous graph in the graph design and in exploratory data analysis history is this plot by Menard. about the French invasion in Russia in 1812. And this is generally thought of as one of the most information-rich graphs that you can find. It's also just kind of beautiful in and of itself. And this is the original graph, and then you can see it's the same thing, but here's a version I grabbed off of Wikipedia that has the English translations on it. And so what this graph depicts is as you go from left to right here, this is showing the French troops as they marched into Russia, starting here and then ending up in Moscow. Down here, you actually see the temperature, okay, and the path actually does quite closely mirror the geographic path that the troops took, right? So that this really does look like the path they were taking. The width of the graph represents the number of troops at that particular time, and you have the troops, and these little breakout things are groups that broke off, right? That tried to go a different direction. And then the black line coming back this way is the retreating troops. So this group, for example, broke off and then they retreated, and this is this retreating group, and this is this retreating group. Okay, and what was interesting historically, what happened was the French had a very strong troop. They started out with collection of troops. They started out with 422,000. Okay, and the Russians had a very very harsh strategy. Is they were going to engage the French troops and then retreat, and then engage them and then retreat, and then as they retreated, they used these scorched earth protocols where they would burn all the fields, and as they retreated, the French troops would have no way to resupply, and so their goal, the way the Russians were going to win this campaign, was just by basically freezing and starving the French troops to death with a war of attrition as the Russian troops just repeatedly fell back toward Moscow. And you can just see with the width here, the way this graph displays the death toll, it's striking. So it started out with 422,000 down to 100,000. You can almost feel, the cold and horror as these troops are trying to cross this river. When they get to 100,000, right, then when they hit Moscow and they get to retreat, and then you see down here back at the beginning 10,000 troops. So a loss of over 400,000 troops in this march. At the same time, you can see the temperature along the bottom axis here, helping show when the temperature spikes caused large troop losses. Anyway, really wonderful graph, and it's just a highlight of how graphs can be used to just used beautifully. At any rate, this is such a famous graph. I thought I'd describe it. Here's another famous plot that really helps us more easily drill down on why plots are inherently useful. So Anscombe was a very famous statistician, and he created a data set where the mean of the x's, the mean of the y's, the correlation between the x's and the y's, and hence the r-squared value and the slope of the regression line, and the standard deviation of the x's, standard deviation of the y's, these were all the same, matched from these graphs. And so if you ran these in a regression model or a correlation, or you did a basic summaries like mean of x, mean of y, standard deviation of x, standard deviation of y, you would get the same answer for each of these four graphs. However, obviously there's very different stories being told by the four graphs. This one looks like a kind of just a regular noisy regression relationship. This one clearly looks like a noise-free parabolic curve. This one looks like a noise-free line with one outlier. This one has almost no variation in the x variable except one point that's way outside of the data cloud. So in all these cases, unless you had done the graph, if you had just done the kind of obvious summaries, you would miss this incredibly different story from each of these four data sets. And he did this exactly to make it as striking as possible. Another great example is Len Stefanski, who's at NC State, likes to trick his students, and he creates these settings where you have a regression model, and if you look, it looks like the variables just follow a nice regression model. There's some significant p-values. And if you fail to do a residual plot, you could just run through the analysis, figure out what variables might be necessary, and see nothing in particular. But what happens is if you plot your predictive versus your residual values for the model he's telling people to start with, you actually get a picture of Bob Dylan in the residuals, and he's written some algorithms that show how you can create whatever picture that you want in the residuals. So he can tell whether his students did the plot or not because they would obviously comment, hey, there was a picture of Bob Dylan in my residuals. So I hope that illustrates some of the important reasons of why we need to do plots. And then I'm basically going to spend the rest of the lecture talking about ways in which we can improve our plots or some pitfalls to avoid. Okay, so as some general principles, one is by Tufte, which is, I think, a really great contribution to the plotting literature, which is to maximize the data to ink ratio. So if you take these slides are from Carl Broman. I don't see it noted on here, but I'll add that. Carl Broman is a faculty member at Wisconsin who's a real expert in exploratory data analysis. So here you have this great plot where you have a response plotted by the treatment versus control. It has incredible data to ink ratio because it displays all of the data with very little ink, and then it has this nice mean plus 2 standard deviation confidence intervals for the two groups. An incredible amount of information, recreates the whole data set in one simple plot. In contrast, you could do this plot as a bar chart, 2 bar charts, and then look at the amount of ink you're using effectively to display 2 numbers, the mean for the treatment and the mean for the control. Just the loss of information going from left to right in these 2 plots is simply incredible, but also the increase in the amount of toner from your cartridge that you need to get the second plot to display 2 numbers that you could have just put in a paper or whatever anyway is almost ludicrous. So that's the principle that Tufte is trying to elucidate, is try to create plots like this one on the left where you display the data as much as you can, and when in doubt, try to devote ink to data. I think probably a useful way to put it would be information to ink ratio. You want every bit of ink you're using to display important information. This gray background isn't adding anything. Most of these lines aren't adding anything on the right plot. The purple, it's just, this is not a very informative plot. It's just basically displaying 2 numbers. Another general principle is don't use 3D. So here we've taken that same plot and we've basically ruined it even further by adding 3D. You have this optical illusion of this corner here that doesn't add anything either. And just to really highlight the principle of why you shouldn't use 3D, we can basically take this plot and remove all information by the angle at which we look at it. So, and this just is hard to bring it to the point of ludicrousness, where you're looking straight down at it, and of course now we don't even display our 2 numbers. This is just, we've removed all information content from our graph. But that's also showing that as you take this 3D plot and rotate it a little bit, you're losing information. Now, I work in brain imaging, and very often we use 3D because the brain is a 3-dimensional object, and we're using it very carefully to try and display information. But I think you can say a general principle is that for ordinary plots, don't use 3D. Another thing is logging. So taking the natural log or a log base 2 or a log base 10 can be crucial if the scale, if orders of magnitude are important. So here's an example that Carl came up with in a genomic setting. You can see on the right-hand side of this plot, it's log base 10, and you see this interesting variation in separation between the groups with a lot of information. Here's the same data set unlogged, and you see basically it looks like everything's 0. So if it is the case that orders of magnitude are important, like, take, for example, an obvious setting like astronomical distances. You obviously care more there about orders of magnitude than anything else. If orders of magnitude are important, then if you look at this plot in the way on the right, you've lost all the relevant information by not taking logs. So at any rate, taking logs is often a very important thing to do. Here's another example Carl came up with, and this is a mean difference plot on the log scale. So it's the log of the ratio of 2 gene expression levels, and then it's the average of the 2 gene expression levels. And you see all this interesting variation on this plot Also, what this does is it takes the scatter plot. You might think, well, I could plot log expression level 1 by log expression level 2 in a scatter plot. This basically does the same thing, but rotates it 45 degrees to get rid of the unnecessary blank space. And you can see interesting patterns, such as the variance of the difference decreasing by the increase in the average log expression rate. But you can also see the bulk of the data, it's spread out in a nice way. If, for example, you were to plot this unlogged as a scatter plot, first of all, you have all this unnecessary white space above and below the collection of data. But as Carl points out, 99% of the data is below this red line. Okay, so you might look at this plot and come to some conclusions, but you're really only looking at 1% of the data. Okay, so now the last thing I'd like to talk about, I have about maybe 15 minutes left, is kind of the psychology of plots. There's a science of plots. So let me just talk about, for exploratory plots, what are some general characteristics. So usually you're making them quickly. You're not finalizing. So I'm not going to talk about design today, right? Like there could be an aspect of, once you've got a plot that conveys all the information that you want, how do you get it into a super nice design for a reader for publication? Okay, that's different than what goes on in exploratory plots. The plots are usually made for you or your team, right, as you're going through the data. So the goal is for personal understanding. And a large number of plots are made. They're made quickly. Generally, it is worth spending some time labeling your axes. So if you can not only have your axes labeled, but also have the units of the measurement on the axis, that is generally better. But also the axis and the tick marks and things like that are usually cleaned up, because otherwise we'll see that that's a really easy way to make plots difficult to understand, is to not have spent any time on your axes. And then colors and size are primarily used for information. Like I said, you're not spending, in exploratory data analysis, you're not spending a lot of time on final colors and things like that are used to make it look nice for presentation. You're spending more time on information. So especially for plotting, there is a, not terribly well developed, but at least a nice history and some great research in what I would call a theory of EDA. And what I mean by theory of EDA, I don't actually mean the mathematical theory that underlies some characteristics of plots. That exists, of course, and that's super well developed. But what I'm talking about is the psychological part of EDA, how we perceive plots. And it's unfortunately true that we're designed to find patterns even when there aren't any. And our visual perception is then biased by this humanness. And so, again, the goal in EDA, just like we discussed earlier, is not to fool yourself. And the real pioneer in this field is Bill Cleveland, at least in the field of statistics. I think it's a much bigger research area now, but in the field of statistics, he was a real pioneer of it. So I'm going to talk about some of his early work. But just to get us in the mood, let me show you some slides where we see some optical illusions, which could very realistically occur. Something like this could very realistically occur in an exploratory data analysis. So in this optical illusion, these two middle points are of the same size. But of course, because of the size and distance of the surrounding points, we perceive them to be different in size, typically thinking this one's smaller. This is sort of some unintended framing that's sort of happening. So that's one example. This one is, I think, this one drives me nuts, but you can load up this image into Photoshop or whatever and check it yourself. But the A and B squares in this plot are actually the same tone of gray, which is I find amazing. So the surrounding colors around, and this is achieved by the shadowing effect. But again, the idea is that even if you're trying to compare something in a plot by tone, we can actually have instances where our perception is very much so off by with respect to tone, and the optical illusions just hone in on this as and make it as bad as it can possibly be to highlight this principle. Another important point, just to return to this point about multiplicity and testing things until you find something that's true. Hadley-Wickham actually does exactly formalize this concept, and we have there's a link down there where you take, for example, a data set. Let's say this middle one is the real data. He actually then permutes and plots some examples of the permuted data set so that you can sort of visually perform a hypothesis test. So he's formalizing this idea of a hypothesis test done on data. However, this point illustrates to us that whenever we do a plot, whenever we make a decision and then do another plot, and make a decision and do another plot, these are informal hypothesis tests. These are informal models that we're fitting. And so all the problems that exist that we talk about with formal models and formal hypothesis tests get brought into this process just in a fuzzy way. Okay. Now let me talk about Cleveland's work because it's so fundamental. And so what he starts with in this work, this paper down where I have the link down here, is really the Journal of the American Statistical Association paper is really the foundation of this work, and is really just a fundamental paper in this area. And one thing he brings up is this idea of sort of the DNA of perceptual tasks, these sort of these perceptual units. And he basically says what we're going to do is try and break down graph characteristics into these perceptual units. So like contrasting lengths is an example of a perception task. Comparing angles is an example of a perception task. Comparing direction and area and volume, curvature, shading, position on a common scale, position on non-aligned scale. These are all perception tasks. And the argument he said is, well, we can kind of figure out how people do. We can isolate perception tasks, test how people do on them, and that will back inform what kinds of graphs we should be creating. So take this experiment he did, where he looked at several different types of specific position and length type perception tasks, so in all of these cases, the people were comparing trying to get an idea at the ratio of the length of the ratio of the lengths of the two dotted bars, and they have type 1 where they're right next to each other, another type where they're separated but they're on the same scale in the lowest box. This one they're separated in two histograms. This one they're the top box separated, and this one they're right on top of these others. And then he called this the position and length experiments because some of these are varying position and some of these are varying length comparisons. And when he looks at this, we can see that there are certain kinds of things. This is the log absolute difference between the actual true ratio and what the people he was testing, what they thought it was. So we saw that certain positions were doing better than other ones, and you can kind of guess how it would work on this type 5, the length one, right? That's this one where we're comparing two things that are not next to each other, right? It's very hard to figure out the relationship of these two things because they're not directly comparable. But these two things, type 1, we're doing quite well at when they're right next to each other and on a common, compared with a common axis. So, but he could quantify that, and then he looked at several different perceptual units. As an example, he also looked at volume, ratios of volumes by comparing things like positions or angles. So here would be something like a pie chart where we're comparing angles. If you're comparing the volumes of two things, you're really making that comparison by virtue of the angle of the slice, whereas the bar, he might consider comparing it with the position of the bars. And what they found was, one thing is that these angle comparisons were quite terrible. The log absolute difference for the angle comparisons was quite terrible. Another thing, one of the worst examples was if you had to compare the ratio of two slopes, and they looked at whether different ways of displaying different ways of displaying the two slopes. So you want compare the slope from A to B to the slope from B to C, you want to estimate that ratio. And of course, if you squash it in, it gets harder to do. If you display it vertically rather than horizontally, it gets harder to do. And we're very bad at doing this. But remember, we often make plots where we're plotting the slopes of two groups, and intrinsically we're asking the reader of the plot to perform this calculation. And what this research is showing is how much you squash the plot, how much you stretch it, or even this task to begin with is actually quite difficult for people. Another interesting, and this was a separate paper, another interesting idea was that the scale matters quite a bit of the plot. So as an example, they showed people scatter plots with the same correlation and found people reported dramatically different correlations depending on what they varied. So here, they might show things that have roughly similar correlations, but when they zoom out, people actually say that, estimate, if they visually estimate the correlation, they say that it's higher when you zoom out. Okay, so again, our perception of correlation is dependent on the scale at which the arbitrary scale at which we choose to display the data. Here's the results of this perception task, right? So, of course, if there's zero correlation, people seem to be doing fine. And if there's 100% correlation, people seem to be doing fine. But, here are these plots. The size of the circle kind of represents the variability at that point. You can see, at around correlations around 0.6, 0.5, 0.7 or so, people get the worst. They're the furthest away from what the actual correlation was. These two other lines, I happened to reread this paper last night just to say this, they were trying to figure out what were the best geographic models. So they think this is a model for what people are actually visually modeling rather than this, which is kind of more closer to the truth. So they came up with kind of theories of the geography that they think people might actually be operating with. A good theory of the geography that people appear not to be operating with, and a bad theory of the geography that appears to not exactly go through the data, but appears to more closely correlate with what people are doing. Another great paper was by Jeff Leek, who does some research in this area using our Coursera classes. And he actually had students try the experiment of whether or not they could ascertain significance from a plot, of a correlation from a plot, just by looking at the scatter plot. And one interesting thing they found was that people could not do these kinds of tasks, but you could train them so that they were able to do it. And they broke it down by different categories of how of things that they could change. They broke down the accuracy by different ways in which they changed the way the plot was displayed, axis scale, whether or not they put a low S curve in there, the smaller end versus larger end, and showed versus accuracy. But an interesting component of this article was that they were able to break down, the various components that impacted whether or not people were able to surmise these p-values. But then it also they also saw this training effect. So some basic summaries. Whenever possible, use common scales. One of the perception results was, when you mess up the scales, when you have two plots right next to each other, and one of them's on one scale and the other one's on another scale, that the comparison, that translation mentally is quite difficult for people. So when possible, use position comparisons. Things that are on the same scale in the just measuring. Measuring where they are relative to that scale, basically asking where two things are when they fall in a ruler. Those are the best things that people are the best at. One of the things they were the worst at was angle comparisons. So they're very hard for people to do. And a consequence of this is it basically says that people are no good at interpreting pie charts. Things like we mentioned earlier, adding a third dimension generally doesn't add much, but also decreases from people's ability to perceive things. And then again, this point that I've raised up several times during this lecture is, do not fool yourself about significance. I think I got this slide from Jeff also. He makes an important point about saying in either direction. So we've talked a lot about not fooling ourselves in the terms of not making false positives, but you don't want to then go on the other way. You can avoid all false positives by saying everything's junk. nothing is ever significant, and you don't want to head in that direction either way. You want a good compass, you know, to guide you. I just want to give some acknowledgments. So I got a lot of these slides from Jeff Leek and Carl Broman, and then Jenny Bryan, Ginevra Allen. You know, I got some stuff from XKCD, Wikipedia, Len Stefanski, and RStudio. And then I think I hit exactly 12:45, so I saved some time for questions if there are any.
So thank you, Brian. So if there are any questions, please type them into the question box. Everyone's muted, so they can't actually ask them to keep all 200 people from asking at once. But while we're waiting for more to show up in the question box, I have one to ask you, and that's whether you have an example of where a lack of pre-processing or a lack of looking at your data ahead of time has really led you astray and really messed up your analysis later on.
Well, I think, you know, well, for certainly anyone who teaches a statistics class can give you an instance of when students have written reports, for example, that, you know, when they don't look at values, they get messed up results. So most teachers will do something like spike in some crazy values that'll mess up everyone's results and try and teach people that lesson early. But I think that lesson it's very hard to make that lesson sticky, because I've certainly had many times in my life where I've gone through a full analysis, thought I found something super interesting, you know, kind of started to like write it up with you know, to share with my collaborators, and then found, you know, after, you know, maybe on the way to talk to them, realized, oh no, the direction of the effect is the exact opposite of the direction that I thought it was going to be, and that science would dictate. And then I you know, when I go back, I realize it's always one of these sort of errors that, you know, that like there was some error in pre-processing, there were some missing data that were coded, that was coded as 888 or 999 that I didn't catch, or there was some errant values, like someone who was you know, 200 pounds being put in as 2,000 pounds or something like that. And you know, that also reminds us not only to, you know, do plots, but also checks. You know, there's diagnostics like DF fits and DF betas and things like that that really help us in our models diagnose these errant values, and it's always worthwhile to do those things. So, I mean, I can say pretty much any time I've ever failed to do the common steps of doing a lot of plots, checking my regression diagnostics, every time I don't do that, I always wind up with something screwy, and then it just depends on how far I take it before I have to go back and check it.
Well, that's very good. That's a very good lesson for all of us to learn, is to spend time doing that first. But what about, do you have a sense of like what percentage of your time you spend doing the exploratory analysis versus a confirmatory analysis?
I think that very much so depends on what branch of science that you live in. I think I live in the discovery science world. So when I work on fMRI and MRI, much of my analysis is really on this, you know, discovery side science, and in that setting, I think a lot more of my analysis could be described as exploratory, as more toward the exploratory end. So then I would say for many of those projects, I would say a huge chunk of it is exploratory, 80% or something like that. Now there are other settings I work in where the setting is more mature, and you know, like take an Alzheimer's disease. I think the setting, because there's so many people working in Alzheimer's disease, we have a better kind of compass, scientific compass to lead us. And in those settings, we tend to go into the analysis with more directed hypotheses. And then I spend a lot less time, you know, we tend to be able to come up with a nice frozen data set that really is exactly what we're interested in. more often, when in the other cases, it seems like we start out with a data set that we're interested in, we find some interesting things, and then find that we didn't process the data in the way that was necessary to answer now these new questions that arose, and then we have to reprocess. And I certainly would think that someone who worked in clinical trials would spend a little bit less time on data processing, pre-processing. But I don't know. That would be an interesting empirical study. Would be to actually get actually numbers about it, because I'm sure what we perceive the amount of time we spend on data pre-processing is different than what it actually is.
Yeah, I bet. So we have a couple questions in the question box. The first one is about lasagna plots, going back to the very beginning, and whether lasagna plots violate your data to ink ratio.
They do have a lot of ink. That is true. But on the other hand, they are displaying the full data set. So the numerator and the denominator is high in that case. So I don't know if they have a great data to ink ratio, but they do have at least in our estimation, tolerable one. Especially because they tend to take large data sets, and they tend to they basically redisplay the whole data set. The key with lasagna plots is not so much the original plot, because that's interesting in and of itself, and if you're lucky, like in the sleep experiment where there's some obvious missing data pattern that for whatever the reason was common across subjects, that's great. But probably the key to the lasagna plots is some sort of sorting or organizing your rows where you can try to detect patterns. But anyway, yeah, the point is well taken. That yeah, they do use a lot of ink.
Okay, and then the next question is about any suggestions that you might have for software to do EDA. Do you have any preferences on software, or could you just give some advice about what are some things people might use?
Yeah, so I use R. And then, but I've been using R for a long time, so I use base R, which is just R's default plotting stuff. Since then, in R, there's been a sort of a revolution with this package called ggplot. And ggplot, the ggplot stands for grammar of graphics, and this was a theory that was put forward on worked on by starting back. I think it dates back to Cleveland and other work at Bell Labs, and then goes all the way forward to Hadley Wickham's work on it, and several other people. And then I forget who the actual inventor of the term and the concepts of grammar of graphics. At any rate, this led to a system that is then operationalized in the R package ggplot, which is, I think, one of the most popular R packages. And if you get used to ggplot, people seem to absolutely love it. I use it. I find myself using it more and more, but because I was so used to base R, it's been hard for me to switch over. And ggplot, as implemented in R, basically has two steps. One is you have to work really hard to clean up your data and get it into a nice format. And that's almost a feature of ggplot, in that it forces you to work really hard on your pre-processing before you start plotting. And then once you get it in a nice format, then you're off to the races with the plots. And then the actual plotting syntax is quite good for ggplot. So I would recommend that. But I would say every statistical data analysis program has completely tolerable graphics capabilities, and it's more, I think, I don't think the tool is as much the problem. Now, if you're talking about creating production-ready graphics, then I think you can get into the specifics of various platforms. One thing that I didn't mention that is quite useful is interactive graphics. That's where you create a plot and you create sliders or buttons or dialog boxes and things like that, so that the person who's looking at the plot, whether it's you or whether you're giving it to someone else, can interact with it. And there's increasingly great tools for that, like Plotly is an example, Shiny in R is an example for that, and then of course the gold standard for that is D3, which is the JavaScript library, but that requires a pretty heavy investment of programming knowledge and time to master that. But there's some layers like Plotly that have been built on top of D3 and other libraries that make it kind of easy. So, anyway, I guess to answer the question from my perspective, I use R and I like R. And then if I needed interactive graphics, I would use Shiny or Plotly.
Thanks. And there was a comment in here, not along the lines of software, but other resources. There was a comment in here from Ethan McMahon about a report, an EIA report that he's seen that is useful in this area. Can you, though, in addition to your comments on software, could you give some advice about where someone might go to find out more information about EDA? I mean, you mentioned a couple, some of the leaders in this area, like Hadley Wickham and Carl Broman, Jenny Bryan, Bill Cleveland, and you also mentioned Roger Peng's Coursera course. But other than those, going to the research of the first group or Roger's course, do you have any other advice for where to find more resources? Other than the tolerable book that you could just pick up. I mean, anything that really stands out. So
there's two aspects to EDA, and one is super well developed, and the other is a little more amorphous. So the first aspect to exploratory data analysis is the plotting component to it, and there is I think a lot of great materials on plotting. So on design, there's Tufte's books. On kind of the perception, there's all this Cleveland work. On the implementation, there's lots of books on specific plotting implementation. There was a great book written by Nathan Yao on who does flowing data. Look at his work on graphs. I'm trying to think. Roger Peng has Roger Peng's course has quite a bit of stuff on graphing. Cleveland actually has a book on plotting as well, kind of a Tufte style book on plotting. There is boy, I'm forgetting, I'm blanking on some names, but there's lots of books on plotting. And then there's the other aspect of exploratory data analysis, which I didn't get too far into, which is, you can use models, clustering, huge chunk of tools, kind of what I would just call modeling tools, but in general, statistical tools can also be part of exploratory data analysis. Regression is a key part of exploratory data analysis, right? You add a model, throw in a confounder, check things. So. And I would say that's less well developed as a field. There is, so there, you have to go to books on, machine learning or clustering to look at unsupervised clustering. Any regression class will have lectures on how to use regression, but they won't kind of differentiate the use of regression in EDA versus the use of regression in a final confirmatory type analysis. The standard for that is, of course, Tukey's book. For that style of analysis is Tukey's book. It's wonderful in that regard. So that would be the starting point, and then I'll think about that maybe on the slides, which are Google Docs. I'll add some references if I can think of some more.
Okay, and I think you just answered the last question, which was commenting on whether some other techniques like dimension reduction and collective variable search would be considered EDA or could be categorized as EDA, and that sounds like what you just answered.
Yeah, absolutely. I would consider that EDA. Anything. EDA. I guess one way to define EDA is anything that's not confirmatory data analysis. But I think when I look at my definition, it's a little bit. It's not very strict for what constitutes EDA. And I think I define it more along the lines of if you're really doing hypothesis generation, and you're really kind of doing a more free-flowing style of analysis where you're kind of looking for trends and you're poking and you're prodding and you're kind of developing your hypotheses on the fly. Anytime you do that, no matter what techniques you're using, I think you're doing EDA.
Okay, great. And with that, since we are out of time, I want to thank you again for this great lecture and for coming here to help us understand this better. Thank you, Brian.
Oh, no problem. Thank you.
All right. Bye-bye.
Bye.